all of you for Thanks for all of you for tuning in today. Um, as you heard, I just defended actually this topic just last week. So what you will hear is a bit of a edited version of my dissertation defense. And so I will start off with kind of a broad introduction. So we all get kind of on the same page on that subject. And then I will take a deeper look into the actual results of my time as a PhD student. And so I will present to you in the next 30 to 40 minutes sedimentary tellurium as a novel proxy in order to unravel this intricate link between flop basalt volcanism and mass extinctions. And so I want to start off with introducing you to the term LIPS, which is an acronym for large igneous provinces. And what you can see here on this map is kind of the Phanerozoic distribution of continental flop basalts and oceanic plateaus. And so basically these two features are combined as lips, and what they are is they manifest the largest volcanic features known to Earth with magmatic volumes often exceeding 1 megacubic kilometer. And it's usually thought of that 70% of the total eruptive volumes are also emplaced in rather short emplacement times. So we're talking about less than 1 million years usually here. Chemically, we're looking into mostly mafic compositions that are erupted predominantly in effusive eruptions here. And so when we look at lips associated with mass extinctions, then I want to draw your attention first to this very famous plot, which basically shows you the last 400 million years throughout Earth's history on the x-axis. You see on a first y-axis the generic extinction as a percentage shown in this pinkish U here. And then on the secondary y-axis, you have the emplacement of a variety of lips and their eruptive volumes. And so what you can take from this graph in the first instance is that you see that at least 3 of the 5 biggest mass extinction events, they temporally correlated quite well with the emplacement of such lips. But in fact, so do a variety of minor extinction events or also periods of global perturbations, environmental perturbations in general. Now, despite this temporal coincidence that we're looking at, we kind of face the issue of sometimes having superimposing effects. And certainly most famously for that would be right here at the end Cretaceous and the emplacement of the Deccan traps. Of course, the impact of the Chicxulub meteorite, which is still thought of as kind of the main contributor or agent to the demise of the non-avian dinosaurs. Mm. Now, despite this temporal coincidence, of course, we can also look into what's the causality behind all of this. And when we do that, we can, of course, think about this whole kind of kill mechanism, cause and effect matrix that already shows us that there's a variety of direct and indirect effects coming from such large-scale volcanism that can not only perturb Earth's climate, but then also leading to secondary effects like ocean anoxia and acidification, acidic rain, and so on, and all of these kind of facts that are ultimately tied to large-scale volcanism then can, of course, be linked to terrestrial and marine extinction events. Now, fortunately for us, there's currently no lip emplacement going on, but we can still kind of see the remnants of these large-scale volcanic features. And just for you to have an idea what we're looking at, we still find, for example, the Deccan Traps outcropping here shown in the Western Ghats in India, but then also maybe more famously such tourist attractions as the Giant's Causeway in Northern Ireland, which then is related to the North Atlantic Igneous Province, or short NIPE. Okay, now despite this temporal coincidence, we of course face some issues in finally linking volcanism and environmental perturbations here. And so most of this lies in the fact that we're looking at a lithological dichotomy. So what that basically means is we're having one side of the history being the volcanic history. We have that recorded in magmatic rocks. And so those are the rocks that tell us about eruptive volumes, the styles in which these deposits were erupted. And neatly enough, they can also be directly dated by radiometric age dating methods. But then on the other hand, the whole kind of environmental side of things is recorded in sediments. So those are the rocks that also hold our paleontological record and thus tell us about mass extinctions in the end. However, the actual triggers for such extinction events recorded in sediments, they remain unknown just in the pure lithological record. And given that, in combination with the fact that sediments are mostly dated indirectly, we kind of face a missing link here between cause and effect again. And so one thing we do, or one option that we have to tackle this missing link, is the use of geochemical proxies. And so just in the very basic understanding what the geochemical proxy is or what it does is we're looking at a source process, in this case volcanism, that emits or alters a chemical signal in the environment. That can be either trace element concentration, it can be an isotopic ratio, and so on. And then on the other hand, we have the sediments capturing this unique fingerprint, this chemical fingerprint. And so this gives us the possibility to actually see all these environmental effects in the sediments being linked to the actual source process, which is volcanism in that case. Now, however, to confidently use such geochemical proxies, we have to make sure that for once their actual origin or their source process remains rather singular. So we don't want our potential geochemical proxy be affected by a variety of processes, of course. And then on the sedimentary side of things, we wanted to show very low post-depositional effects. So we don't want anything happen to it with changing environmental conditions and so on. So we want to have a stable sequestrated signal there. And so, of course, we are not the first to actually use geochemical proxies. And ever since 2012, where Hamed Sanayr investigated sedimentary mercury back then as a potential lip proxy, it was shown to be rather popular. And as you can see by the Google Scholar results, ever since then, using mercury as a proxy kind of skyrocketed. Now, nonetheless, we have some issues with mercury. And so basically, most of it stems from the fact that mercury shows a strong affinity to organic matter. And so what people have been doing for quite a while is they have been normalizing mercury to total organic carbon, so the TOC, to tackle this problem. However, we face a first analytical issue with this, considering that measuring TOC below a threshold of about 0.2% gets notoriously difficult and might introduce false positives here into the ratios. But then also it was rather recently shown that the TOC affinity of mercury actually varies with the mercury speciation itself, which then might lead to, while having correlations, actually having multiple such linear correlations in the same data sets. And so all of this kind of obscures the actual use of mercury TOC to some extent and complicates it at least. And then on the other side of things, as I mentioned before with geochemical proxies, the thing is with mercury, we have a lot of non-volcanic secondary processes coming into play here. So when you look at this sketch here, what I want to show you is basically that during times of hypothermia, for example, global warming periods, either lip-related or not, we also have a lot of non-volcanic effects happening, right? So for example, we have an increase in forest fires, we can potentially have thawing of permafrost, ultimately increased continental runoff. With lip events, we also have sometimes tapping of coal deposits, magmatic tapping. And all of these processes lead to a excess in mercury in the atmosphere that is not directly volcanically linked. And so this might be then reflected in our actual sedimentary concentrations that we're looking at. And now last but not least, also mercury has been shown to be quite easily mobilized also during early metamorphism and diagenesis. And so all of this kind of results in the end in the fact that we have, or in the observation that we look at mercury profiles showing volcanic peaks, but not doing so in a uniform or a very comparable manner. So what I show you here is it's several sites spanning the Paleocene, Eocene thermal maximum, sedimentary sites. And what you see is that all of these mercury concentration and also mercury TOC ratios, they do reflect periods of supposed high volcanism, but then they also show high peaks sometimes way before the PETM, sometimes they are completely muted in that area. Sometimes they are just high throughout with not a distinct PETM signal or something like that. So in that case, North Atlantic Igneous Province volcanism seems not to be very well reflected or comparable between these different sites in Mercury. And so all of that led us to actually investigating an alternative. And as the title already said, this is tellurium here. And so what you can see here on this plot is basically a variety of trace elements on the x-axis. And then on the y-axis, you see a gas melt partition coefficient. So all of what you need to know from that, or what you need to take from that graph for now, is that the higher an element sits on the y-axis here, the more it prefers to go into the gas phase in a volcanic eruption rather than staying back in the melt. And so as you can already see here, tellurium is highly enriched in volcanic gases. But then also, as we will show, or as I will show just in a few minutes, there's some other interesting things about it that makes it a nice potential proxy. And so first and foremost, that lies in the fact that tellurium has a very low crustal abundance. And also it seems to be virtually unaffected by any processes regarding changes in environmental conditions. So for example, paleoredox or changes in bioproductivity. And all of these processes have been shown to be a major control on a lot of trace elements, but apparently not for tellurium. And so the only issue that remains with tellurium that I want to present to you before going into the actual results is that first of all there was only one single study prior to this project, so that also makes the data availability a bit scarce. And this has mostly to do with the fact that tellurium has some analytical, I don't want to say issues, but rather complexities to it itself. And so a lot of it stems from the fact, as I mentioned, that it's very low in its overall abundance, which mostly results in low sensitivities. It has a high ionization energy, which is also not super beneficial when measuring using the ICP-MS. And then possibly the largest problem that a lot of people face with it is that it shows various polyatomic interferences in its analytics. So for now, a lot of researchers have used sophisticated methods, just such as sector field ICP-MS or hydride generation ICP-MS, and all of that introduces like a cost and time factor that doesn't make it very interesting to measure it. However, what we found is we have a rather easy and simple method to do it, which basically it all comes down to, of course, wet chemistry, so dilution in the first instant. And then we use a Aridus nebulizer that drastically increases sensitivity, but also gets rid of all our polyatomic interference problems. And then finally, we can just measure it by single quadrupole ICP-MS. And so what we can do with that is we can actually quite confidently measure samples above 10 ppb approximately at very low errors. And in fact, if we actually want to go below this threshold, we can do so with using a simple ion exchange column chemistry procedure before, but this is absolutely not necessary for most of the analyses we do. And so with that, we don't have the need for hydride generation. And what is also quite neat about it is we can measure a lot of trace elements in the same sample solutions and in the same runs. So that gives us the possibility to generate large data sets in a very brief amount of time. And so I just quickly want to show you some results from a study that is actually still ongoing. Um, and what we're doing here is we want to look into more about how tellurium behaves in a general kind of sense in the geosphere. And so we measured the rather large set of different geological materials. So here, for example, we have glacial diamictites or diamictite composites. And these are actually the exact same samples that a lot of researchers have used to estimate decomposition of the upper continental crust. Regarding other elements, though, the isotope ratios. And here we have a set of Deccan lavas as well as red bowls, which are basically these fossil soil horizons interbedded between the lava units. And so what we can show with all of that is that we have a general very good agreement between the 125 and 126 mass of tellurium, which tells us that we're not really looking into any polyatomic interference here at play. And also, we can kind of show that here in the squares is our kind of normal measurement procedure without using any pre-concentration. That even here to around 10 ppb, we have very insignificant errors. That again, if they are expanded with this pre-concentration procedure, we can go down to a few hundred ppts at very confident accuracies and precision. And what we're still doing with that and what's kind of the main take from that, which is also interesting for our next case study that we're looking at, is that these glacial diamictite composites, as I said, they are used to reflect the upper continental crust. So they cover an extensive kind of provenance. So when we measure those and when we look at their evolution through time, we can actually use the exact same methods and data or data work that these authors did to estimate the UCC average regarding all the trace elements, and we actually get to a very first robust estimation of tellurium in the upper continental crust of about 36.7 ppb. So this is kind of the first time and the first value that has been achieved with tellurium with measuring actual samples used for such estimations. And with the red balls, so these fossil soil horizons, on the other hand, what we want to show here basically is what we've also seen in this plot regarding tellurium outgassing. So we see that when we look at these fossil soil sequences, we find that the closer our measurement or our samples go towards the fresh basalt, they seem to be very low in tellurium concentrations, while the actual sediment part of it or the fossil soil part of it in between is the one that captures tellurium during eruption or ongoing eruption of the Deccan province. And it shows us that there must have been an excess of atmospheric tellurium very close by with such high values that are being achieved here in these clay and repo layers. And so with all of that, we kind of have a base understanding of magmatic outgassing versus sedimentary sequestration in the actual volcanic source that we're looking at. Now, however, for us, it's more interesting to actually go into the case study that preceded that work, in fact. And so all of what I'm going to show you next stems from this work earlier published this year. And so what we're looking at here, or what we looked into, is basically a whole sedimentary sequence spanning a rather long time span all the way from the late Maastrichtian up to the early Eocene, situated on what is now the peninsula of Sinai. So it's called the Wadi Nukul section. And the very neat thing about this section is that it actually encompasses two lip events. So we have right here around the KPB, we have the emplacement of the Deccan traps on the subcontinent of India here about 66 million years ago. And then up here on the Paleocene-Eocene boundary is the PETM related to the emplacement of the North Atlantic igneous province about 56 million years ago. And so we not only have lips, we find in this section one of the possibly most famous extinction intervals, so the end Cretaceous extinction, which is also the demise of the dinosaurs, basically. We have a period of global hyperthermia here, the so-called Paleocene-Eocene thermal maximum, as well as other um, global warming events, as for example, the late Maastrichtian warming event sitting somewhere down here. So all of that makes this section quite interesting as a case study for using tellurium as a potential proxy. And so when we dive into the results, into the trace elements, especially of those of our proposed volcanic proxies, tellurium, what we see is when we look now at the kind of chemostratigraphy throughout this profile, we see in a first order very nice distinct trends with tellurium, both here around the KPB, but then also up here an intense spike at the PETM. And all of that while Mercury, for example, doesn't show the same kind of evolutions around the KPB. Um, However, at the PETM again, we also find a distinct Mercury spike. And so another thing that I want to draw some attention to here is that we see a lot of stuff happening, so to say, with the major oxides here in our profile, which basically reflect our sediment composition and the changes in our sediment composition. And so from a first glance, you can see that thorium as a trace element seems to be rather similar to whatever aluminium is doing here. And so this also begs the question for us, in what order the sediment composition and thus major oxides have a potential control on our trace elements, because that's all of the things we have to figure out before actually getting to the interpretation of tellurium as a volcanic signal. And so what we take from that is that when we look at the major oxides and thorium in comparison, we find, for example, that when we plot aluminium against calcium, we find a nice negative correlation, which just stems from the fact that we're looking at two sediment composition end members. So basically kind of the carbonate end member side down here, while up here is the detrital component that also reflects kind of the clay input. And so when we think about thorium in this context, then we can see that thorium is negligible in its content in carbonate. So it mainly stems from the clay fraction. And so we can kind of use it as a control on the detrital input, which gets more clear if we look at thorium against aluminium, where we see this very nice positive correlation. And so the reason we're doing this and the reason we're using it is basically that we now have a normalizing agent for our other trace elements. So that means by normalizing our trace elements to thorium, we can for once control any diluting effects by carbonate or excess biogenic silica, for example. But then also we can account for changes in detrital input, because supposedly what is not volcanic in our tellurium signal has to be from a detrital input. So would the detrital input change the tellurium signal drastically, we'd also expect to have a very high amount of thorium in the system. So normalizing can potentially counter that effect. And so when we now look at tellurium and tellurium-thorium ratios in our chemostratigraphy, we see that they're very alike. And so what this tells us basically is exactly what we want, that the whole system or the whole tellurium kind of changes are regulated by tellurium changes rather than by thorium changes. And so that gets even more clear if we cross-plot those elements, where we see that during these non-volcanic periods, so we labeled them pre-event and post-KPB, we have kind of a linear correlation reflecting the background influx of continental tellurium and thorium. But then as soon as we get into phases of lip emplacement, we have an excess in tellurium. The other thing we need to check for with potential proxies is always what is changing of the environment doing to our trace element signal. And so what we do here is we look into proxies that have been established as being indicative of changes in paleoredox, as molybdenum, for example. And again, both times we normalize it for the reasons that I've just explained. And on the other hand, trace elements that are indicative of changes in bioproductivity, as for example, zinc here. And so what you can see here is that they clearly do not show the same trends and effects as tellurium, except for maybe molybdenum with a peak on the PETM here, which, however, correlation again doesn't mean causality, because we know that there's been anoxia reported there, plus the fact that molybdenum is actually also to some extent enriched in volcanic gases. So we rather believe that this is a correlation that's not meant to show you causality. And this gets even more clear again if we cross-plot things. We see that tellurium-thorium ratios do not change systematically with molybdenum-thorium. Rather, they show us an excess whenever volcanism is at its highest. And so the same goes for zinc. Again, even though you could argue that in non-volcanic effects, you have a somewhat moderate correlation, just showing you the runoff trends. Okay, and so one last thing we can do with our data is we can consider changes in sedimentation rate, which might be important. So basically what this little sketch shows you is that during absence of any environmental crises or drastic changes, you will have a continental tellurium-thorium ratio into your sedimentary system with rather constant sedimentation rates. And so whenever you get drastic environmental change, however, or lip volcanism, you have an excess both in tellurium, but then also potentially in thorium due to the increased runoff. And thus you have a changed tellurium-thorium signal that might again kind of alter your overall sedimentary record and lead you to a dilution or a kind of enrichment that is not in the first order volcanic. And so what we want to do and what we can do is we can calculate tellurium fluxes with using some age data, be it directly from ash layers or from indirect methods like cyclostratigraphy. We can use age models and then with a simple calculation remove kind of the assumed detrital part of tellurium. And all of that gives us a flux over time, as shown here again on the x-axis with time, and on the y-axis tellurium and mercury fluxes. And what we can use it for in the end is, of course, on one hand, we see the highest fluxes are always associated, or are in this case associated with lip magmatism. So around 66 million years ago with the Deccan sequences, and then again at about 56 million years ago with the breakup phase of the North Atlantic and thus Naip volcanism. And now a neat thing we can do with these fluxes is we can actually use them to calculate the integrals, which when we do that for the second spike here, which often is related to the most voluminous eruptions of the Deccan province, we get about 63% of the total eruptive volume sitting in that spike. And this also is very well comparable with geochronological studies that have shown about 70% before. The other thing that is quite interesting for us, it's that tellurium fluxes are virtually muted in the places in between. So when no lip volcanism is ongoing, we don't see high fluxes. However, we do so for mercury, which again begs the question, is mercury affected by non-volcanic processes? And so all of that leads us to some implications that we can draw, especially when we now compare our tellurium-thorium ratios, for example, with geochronological data here from UPB studies from Schöne. And so what we can see is that our initial rise in tellurium-thorium ratios, they kind of indicate, or they correlate well with the late Maastrichtian warming event, as well as with the geochronological data to the onset of Deccan magmatism. But we also see that the highest peak starts rising before the KPB, which tells us that, for example, there couldn't have been a shift in volcanism due to impact, which was also postulated before. And finally, our data clearly indicates that the eruption of these Deccan basalts happened in a rather semi-continuous pulse style behavior rather than in steps. as was suggested by, for example, argon-argon studies. So here's kind of the counter side to the UPB side. So here we look at argon-argon of the same stratigraphy. And again, what we tell from our data is that the placement these authors had for the KPB in the lava pile, so not in the sediments, so the KPB placement in the lava pile, has to be clearly corrected because the highest values are already kind of ongoing in the sedimentary section and do not post-date the KPB distinctly. And so all of that kind of leads us to the assumption that high stress on the biosphere could have been present, volcanic-driven stress, and could have amplified the kind of killing effects by the Chicxulub loop impact in the end. Similarly, for the PETM, we can draw some conclusions when we especially compare our data against carbon isotope excursions and again, the sea surface temperature here. What we see here is that the highest tellurium-thorium ratios, they broadly overlap with the negative carbon isotope excursion. However, the highest tellurium-thorium ratios, they post-date the actual PETM or the CIE peak slightly. So what we tell from that is that while magmatism must have been a clear driver in the negative carbon record, we postulate that indirect magmatic effects were the initial reason for the CIE excursion, while volcanic degassing finally might have amplified this distinct negative peak. And so again, looking at all of that, comparing to the temperatures, we again can draw a conclusion that magmatism, both by indirect and also direct effects, possibly had a large influence on kind of the minor extinction related to the PETM and also the migration events and all of these environmental consequences that came with the period of global warming here. And so just to summarize that up, what we've shown with these studies is that we have the geochemical tools to kind of counter all the issues that can affect our potential proxy, being tellurium here. And using that, we could have shown that the late Maastrichtian warming event coincided with initiating Deccan volcanism, but also that this Deccan volcanism, this most intense phase, it preceded the impact, and so volcanic stress could have very well amplified the effects by the impact here. And finally, as I just showed you, we believe that short-lived intense night volcanism triggered the negative carbon isotope excursion, although indirect effects were possibly or potentially the causing effect for the first initiation of this light carbon injection. And so overall, we believe that we've shown that sedimentary tellurium is a very reliable proxy for lip volcanism, often also exceeding the potential of mercury. And with the fluxes that we show, we can actually use it now to approximate eruptive volumes, which is quite a nice thing. So we can look beyond the possibilities of geochronological data. And yeah, using that, we've shown that the sedimentary tellurium actually ties lip volcanism to the environmental crises, both at the end Cretaceous period as well as the Paleocene-Eocene boundary. And so the things we still face, the issues that we're still looking into, is that overall the knowledge about tellurium in the environment is it's very scarce. And so we know very little about atmospheric residence times. We know not that much about the mantle composition of tellurium. And so all of that kind of leads us to the point where we need to acknowledge that there's just a lot of work that needs to be done to understand tellurium better, both in the geosphere as well as in the atmosphere, and finally also in the biosphere. However, we think that with these studies, we've shown that it is a promising proxy. So we think it's necessary to investigate more extinction horizons, more sites also, and maybe expand these investigation also to the southern hemisphere where we haven't done any studies so far. And then also we could look into historical volcanism, potentially also checking tellurium in ice cores or lake sediments. Well, and finally, as is happening with mercury at the moment too, we could also look into tellurium isotopes to kind of gather a better understanding about the fractionation trends in the volcanic degassing domain, for example. And then finally, also potentially identifying an extraterrestrial signature on our tellurium. Okay, so that was it from me. So thanks a lot for listening here, and I'm open to questions.